stvari, moja karijera je počela otprilike nekih 35 godina u Banja Luci. Ja sam bio član raketnog kluba. I onda u jednom trenutku mi smo odlučili da dizajniramo novo raketno gorivo. I ideja je u stvari bila da se proda nasito raketno gorivo. Raketno gorivo imalo samo dva sastojka. Potassium nitrate i šećer. I mi smo to našli neki mali koher, skuvali smo malo šećera, karamel je postao, imali smo bešavnu cijev jednu, nabili smo to dobro bešavnom cijevi, jedan tokar u blizini nas je napravio nozlu. Nismo imali fitilja, smo uzeli oko metar salotepa, posuli sa lovačkim barutom, stavili u motor, zapali na jednoj strani. Bum! Masivna eksplozija. Ja sam bio bliže motoru, jedan komad gelera je udario mog kolegu u vrat, drugi u nogu. Nisu bile ozbiljne povrede, ali to je bilo moje prvo iskustvo sa raketnim motorima i aerospace industrijom i tad sam vrlo brzo naučio u stvari šta je hub stres na bešavnoj cijevi. Naučio sam da je u stvari hub stres veći nego longitudinal stres. Tonight we're going to talk about S5P, Sentinel-5 Precursor spacecraft, which was built by Airbus and Dutch Space Center. Sentinel-5 is a part of the Copernicus program. It's a spacecraft which has to fill in the data between gaps when Envisat is finishes and the Sentinel-5P, not Precursor, Sentinel-5P is starting. And there's about 5 to 6 years gap. And the mission objectives is really to look at the chemistry of the atmosphere, to look at the air quality, ozone, climates, to sense nitrogen dioxide, sulfur dioxide, aerosol, and other gases in the atmosphere. So it's really a mission. The reason is that we have to design a spacecraft, a specific spacecraft for this mission is that we lost Envisat in 2012. We don't know really why we lost Envisat. This is the picture of Envisat on orbit, just cruising livelessly. And it's taken from another French spacecraft, Pléiades, from about 100-kilometer distance. NASA mission OMI is also finishing their service, and there is a gap in continuous data recovery or data monitoring of the atmosphere. Danko, where is it this one, is it? Oh, this one. Okay. Now I'm scary. Is it the right way? Okay. So now it's about some mission dates, mission details. We are going into now sun-synchronous orbits, and its altitude just about 800 kilometers, and inclination angle is about 98 degrees. So the polar orbit is lifted above the North Pole and goes past by 8 degrees. This is what we called retrograde orbits, because when you look at the North Pole, the Earth is rotating that way towards the east, but when you look at the spacecraft, projection of the spacecraft, it has opposite sense. So we call it a retrograde orbit. Orbit repeat cycle is 17 days, so after 70 days the spacecraft will come to the same point. The swath width. The swath is an angle projection on the Earth from the spacecraft which covers the ground. So if I'm instruments looking down on the Earth, what I've seen on the Earth, this is a swath distance, and it covers about 2,600 kilometers. Data collection, science data collection per orbit is about 92 kilometers. Data downlink is normally once per orbit. Operational lifetime is about 7 years, although we carry consumables for the 10 years. What does tropomi mean? Tropomi is actually this yellow thing. It's instrument designed by the Dutch Space Center in cooperation by other industry. We're going to talk that a little bit later. What troponomy means is tropospheric monitoring instrument, and observation mode is nadir. That means that the spacecraft Z-axis in our convention, in other countries, other organizations, they have different conventions, but our convention is that the Z-axis is longitudinal axis of the spacecraft. The mass of the troponomy is 200 kilograms, and the mass of the spacecraft together with the troponomy is about 900 kilometers. And the contractor was Airbus. I need to explain something to us. This is for spacecraft is a payload or instrument. Below instrument, we call it bus or platform. In some literatures, or some people in UK, they call it spacecraft platform. Okay, so this is a ground segment of the mission. This is S5P. The data will be downloading on 3 ground stations. One of them is Kiruna, node positioned in Sweden, and another 2 is a Svobod, the same like IS-2 mission, and also Inuvik in Canada. The flight data is passed to ESOC in Darmstadt. ESOC is our ESA's operation center, where all spacecraft all flight operations are happening in Darmstadt. And the science data is passed to DLR in Germany, and then post-process data is going to pass to Copernicus industry and to the end users. All data coming from the Copernicus and Sentinel-5 are free for use. Everyone on us can access the data. So this is a typical life cycle of design life cycle of the spacecraft. It goes for the phases. There's a distinguished phase for each phase of the design and each phase of the build. And someone decided to call it from phase 0 and phase A, B, C, D, E, and F. The first phase is most of the efforts from the designers are focused on pinning down and putting down the requirements, the mission requirements. Once the mission requirements are drawn down, then all these requirements are passed down to the spacecraft requirements, equipment requirements, subsystem requirements, and so on. But also at each phase, you will see some design reviews. So at the phase of 0 is mission design review. At the phase of A is preliminary requirements review. Then we have system level requirements review. This is the requirements when we really freeze requirements for the spacecraft. Okay, it's going to be a little bit TBC, TBD to be confirmed or to be defined, but most of the requirements should be at SRR, and then we got PDR and CDR, critical design review. This is a very critical point. This is the point where the agency or spacecraft integrator will decide we're going to cancel the mission or we're going to go ahead. We start cutting material. And it's not happened, it's sometimes happened that really the mission is cancelled at this design. And in some cases, we just don't pass CDR. Sometimes we don't pass PDR, we have to do delta PDR if the customer is not satisfied, or we have to do delta CDR. And then we go to build a spacecraft, qualification campaign, launch, flight readiness review, end of operation review, and at the end is mission closeout review. So now we will, at each of these details, we're going to look a little bit in more details. But this is a classical system level engineering V-shaped flow. where all these PDR, CDRs, design review will be held at each supplier levels, at each tier. In Airbus, we don't try to go below tier 3 because we can't control the materials coming in. So we stop at the tier 3. But all these design reviews and the phases will be happening at each level. On the right-hand side is V-shaped, and it illustrates how design requirements are passed down to equipment. So we're going from mission requirements, some requirements from mission requirements passed down to the system requirements as a spacecraft, subsystem, unit, and then when design is finished at that level, qualification and verification goes in opposite direction. So we first verify units, then we verify subsystem, verify system, and goes at the end is a mission verification, which is actually closed out mission. So the spacecraft bus, which is a platform, this is spacecraft bus without this, with solar rays on. This is what we contract to, we got a contract to build without this. And you can see the consortium. That particular spacecraft bus has been flown before, is not specifically built for this mission, but it was tailored for this mission. It was tailored to support the payload. You can see that most of the components actually coming from Germany, but it's not because of the geo-return. It's because we had long-term agreement with some of the German company to supply components to us. So it was a 50-50. 50% of the equipment was coming from Heritage, as already previously supplied to AS250 platform, but 50% was what is called best practice competition, where they would issue ITT invitation to tender on their website, and anyone from Europe can bid to supply that equipment. Now, this is just to give you a sense of the instrument consortium. We didn't have much visibility of what's going to happen, but I found this picture, so I thought it's quite interesting. So you can see the instrument, it was driven by Dutch space agency. There is a few parts or equipment of the instrument developed in UK as the SSTL Survey Satellite company, and most of the equipment, again, it's coming from the Germany, but whole instrument, this is yellow box, was assembled in Dutch space, in Holland. By the way, all spacecraft was 3D printed out of the plastic, and you'll see later on instrument as well inside, when we start talking about the structure and configuration of the spacecraft. Right. This is quite amusing picture how we look at ourselves as a part of the team. So I'll be probably declare myself as a structural designer or structural engineer, mechanical architect, and this is how I see the spacecraft. I really don't care about the propulsion. I don't care about electronics, black boxes. I need to make the spacecraft to survive the launch. For me, strength is everything. As opposed to the power designers, they don't really give a damn about the structure. All they want, solar array power as big as they could. But this is sometimes when we're all making mistake and we just don't see a big picture. Don't see a big picture of the spacecraft, and then really just at the remit of our own responsibility. In fact, the spacecraft is really compromised of all requirements, and we sometimes need to make a compromise with our colleagues, engineers, to make their life easier, if we can. So it's all about compromise, just like in a marriage. Right, so we are starting now with the phase 0. And phase 0 is normally called a study phase. You can see on the right-hand side how we started. This is image of the spacecraft Sentinel-5, how it looked at phase 0, and this is sort of look how it's finished. So there's not much really similarities between these two. So it's primarily top-level activities between agency, a spacecraft integrator, and science community and other organizations. Then we try to develop the preliminary technical requirements, identify possible mission concepts, whether we go into polar orbits, whether we go into geostationary orbit, or maybe in the more near orbits. Russians, they prefer more near orbits. Assessments of the payload technical readiness level. We need to see what has been flown before and whether we can build on that experience and that knowledge. And also we will do a preliminary risk assessment. Say, can we perceive the risk coming towards us? Can we see just on the horizon? Or can some more experienced engineers like myself, can we look around the corner what's coming towards us? And at the end, we will develop a mission statement. A release of the mission statement and the access of the preliminary technical requirements, specification, and programmatic aspects. And these mission statements, when you see these requirements, is always repeated in the most of the requirements. This mission requirements, why we're going to build the spacecraft, and what it's going to do. At the end of the phase 0, we'll have a mission design review. And at this point, for the Sentinel-5, but it doesn't need to be practice for the old spacecraft, the agency issued ITT, invitation to tender. And that was a specific one because two companies in Europe, they bid for the same job. It was, at that time, was Airbus and OHB, previously called Airbus, previously called Astrium. So we had to create a bid team. A bid team work on the creating a bid, which we later on supplied to the agency. So we went through a lot of iterations. Iteration change all concept of the spacecraft. And then at the end, at the top level, probably just system engineer, engineering manager, they would go to the agency and they review the system requirements, the top requirements. And at that point, system requirements is a frozen, no change. This is it. This is the gospel now. We can't change system requirements anymore. If we change the system requirements, it's become very costly. Okay? Right, so you are still in the phase A. And you can see now how the spacecraft architecture, the geometrical model, starting to look like the real stuff. Okay. At this stage, we wouldn't have still information about geometry of the model. We wouldn't have full information about geometry of the solar rays or equipment. So what we do, we just put what we call allowable volumes. We just put a placeholder in the spacecraft. Just our designers, CATIA guys, they will put just a box, say, well, that box is OBC, onboard computer. Right, at that point is PDHU or any other equipment. In fact, at this stage, we didn't have even information about solar rays because it hasn't been designed yet, but we did know what is power requirements. Our power engineers, they sized the solar rays. Actually, this solar rays is a size about 1.75 by 1.24 meters. So they know what's the size required to support the mission, to support the payload, but we don't know the details. So we just put allowable volumes. At this point, we will start issuing what we call a request for information. If equipments are coming from a different supplier than from long-term agreement suppliers, that would be placed on the ESA website called EBIT. And we would normally approach suppliers and send them requests for information. We will ask them basically, have you ever built something similar? If you have, give us information, give us roughly what you have been built so far, describe, and roughly what is cost to be. So we want to gauge them whether they are capable to build something similar. But also afterwards we will send a request for quotation, and that is a request for quotation where we ask them for the firm ceiling price to supply the equipment or subsystem. Right, so this is at the end of the PDR. The process of the PDR is it's come to sort of preliminary design review. It's not going to be exact, but preliminary. We would have sort of feeling whether this design would work. At that point, we would decide which verification approach we're going to use. Whether we're going to build breadboard, engineering model, or maybe STM model, or what is going to be a whole spacecraft verification approach, whether it's FM model or PFM. BB is breadboard engineering model, STM structural thermal model, and FM is the flight model, and PFM is proto-flight model. When we put them on the shaker, when we verify these models, they all have different levels, verification levels. Flight model would have the lowest verification levels, and qualification models would have the highest. Breadboard is the model which just give us a proof of the concept. Engineering model we would build probably just from the commercial materials and see roughly whether it's going to work or not. Then we would update PDR data, update technical requirements, and then a PDR data pack is sent to the agency to review, right? And then ESA will take all the data pack and then turn every single stone in that data pack and come to us with loads of questions. And we call this question a RIT, request for information or discrepancy. And sometimes they would generate hundreds on the bigger mission. This is a small mission, but it could be 1,000 questions. And we would carry this question almost to the flight readiness review. We just don't have time to review all this. We try to review as we go, but we just can't physically respond to all questions. After PDI is submitted, then we all go to ESTEC and we present the review to the agency. And at that point, this is the first point where we try to kill as much as possible these RITs right there. If we are successful at the PDR, then the agency will say, okay, we are happy with the design so far. Your design is mature enough. You can proceed now to the phase C. Sometimes the agency will say, well, no, we are not happy. You need a little bit more work to do, and we will have a delta PDR, a delta review. Now we come into the phase C. At the end of the phase C is design review called critical design review. And the mission area, this is really very important milestone in design of the spacecraft. It's a point where you decide, or someone else will decide for you, whether to carry on project through to go to the assembly of the spacecraft, or you stop there and wait better days. In terms of analysis, we just turn the handle again. We do all analysis, we did a PDR, but now, after PDR, we learn something. So we update our models, we review our assumptions and our models mechanical models, FEM models, or thermal models, or AOCS models, they look differently. We learned from results from the first cut of analysis. So we're all busy now updating our assumptions, updating our models, turning the handles again, going through the same motions again, and again we generate a data pack. We send data back again to the agency, they review the data pack, they raise again the reads, we again go back to STEC, we present our designs, try to shoot as many as possible these reads to kill them straight away, and ESA will decide, right guys, our design is mature enough, you can start cutting the materials, or they can say, stop. They just put a plug. Right. We need, once we start for the motion of analysis of the spacecraft, one of the first tasks is we need to check whether our spacecraft can fit into the fairing. On the left-hand side is a Vega fairing, and on the right-hand side is a rocket fairing. We get this data from the launch vehicle user manual. Our rocket was a primary launcher, and Vega was at the time, when we started this design, Vega didn't have a maiden launch first, maiden flight. So it was still on development, sort of qualification, development and qualification cycle. So the spacecraft wet mass was 928 degrees, so you need to go to user manual and say what is the maximum lift of mass, where the rocket can lift that 1,000 kilogram of the mass and deliver into orbits of just above 800 kilometers. So we declared, to give us a bit of margin, we declared, okay, we're building a spacecraft which can deliver 1 ton of the mass to the orbits. So we had about mass margin about 72 kilograms. Right, we had a problem here. When we build a spacecraft, now when we designed the spacecraft, when our CATIA guys, designers, when assembled all components, and when we look at the fairing, we had a clash somewhere towards the end of the spacecraft. One of our antenna was clashing with dynamic volume of the fairing, and that was a panic button. That means we can't fly because we are not compliant with the volume. So we had a bit of discussion, and someone said, "Oh, why don't we call in a rocket guys and see whether they clock fairings?" So we sent an email to our launch vehicle authority. I said, "Yeah, that's no problem. We can sort it out. We'll just clock out the fairings, and the problem is solved." Right. So we talked about analysis campaign. I do apologize. I knew that scheme on the right-hand side is not going to come out good. But just to show you, just to give you a flavor of complexity analysis we do and how we have to interact with other teams. We have to interact. For example, if we have a solar race and the power guys, they change the size of the solar rays, so they say, okay, now it's 1.75 meters, we need to go to the 2 meters. That influences my analysis because immediately I need to give instructions to a mechanical analyst to update his FEM model, to run analysis again, and we need to pass that information to the thermal guy because thermal guy will update his model and pass information to AOCS guy. So there's knock-on effect if you change something. So everyone needs to know that change has happened. But sometimes we just have no time to do that. So what we do, we have weekly meetings. We call it DMU meetings, digital mock-up meetings. And we come to something like here, and they look at the models on the big screen. And we turn the models around and we look at all components that are in place. There's no clashes with the field of view. There's no clashes with envelope of the rocket. There's no clashes with hardness or anything else. And we then just freeze the model and say, this is it. The model is frozen. No one is allowed to change the geometry model. And that is a reference point now. From that model, thermal engineers, mechanical engineers, AOCSME engineers, they will all use the same model. So in mechanical architecture, we are like a Roman god Januaries. We are multi-phased. We're facing so many subsystems, but we are actually a backbone of the spacecraft. We provide support to the equipment. We provide support to the payload. We provide support to thermal equipment. So if I open this, I'll bring it here to you and open these panels and open this and that and this. There's one more here, is it? Go. That's it. That's about right. So we distinguish three types of the structures. We distinguish a primary structure, which is the structure which carries the load. Then we decide what is a secondary structure. And secondary structure will be like small bracketry here or there. Or sometimes we have what's called a tertiary structure. And tertiary structure is like small studs which support MLI, like this multi-layer insulation. Normally, studs are designed just by hand, and you do quick calculation on the back of your cigarette spark in there. It's fine, finger there, it's going to work. Oh, my propulsion module is counted. Okay, but the primary and secondary structure needs to be properly and thoroughly looked into. So one of the first tasks for mechanical engineer is to look at the launch vehicle interface. We need to look how we can actually mount the spacecraft at the launcher. So we look at later on at the bottom. It's called this round circle here, launcher interface ring. But also we look, whether we can accommodate all spacecraft into launch vehicle fairing. So we look at the mounting and alignment of the equipment, the payloads. Load paths, we use a mechanical analytical tool called Nastran, which is mostly popular to industry standards. We look at the stiffness requirements. Stiffness requirements is coming from user manual. In the user manual, each launch vehicle will tell you what is the minimum required stiffness of the spacecraft in lateral, but also in axial. We looked at the environmental protection, how to protect inside equipment from radiation, from the meteor showers. But also we provide a thermal and electrical path to the spacecraft. All equipment has to be grounded, so we provide a grounding point from equipment down to the spacecraft panels. But it's not only that. We need to make sure that whatever we design is manufacturable and we can assemble. And this is what we call design for manufacture. We need to make sure that all will be designed, all we analyze actually can be made. Right, so I have brought some little pieces for you. I'm going to pass around. So this piece is here is a test sample for pull-out inserts. So we do the strength conformation verification of the strength of this insert, pull-out, and also shear. And you will see a cross-section of that insert, and you will see consistency of the potting material of this insert. So this is what we call a honeycomb sandwich panel. It's all aluminium skin. And also, if you have good eyes, and you look better, maybe not this lighting, you'll see tiny little holes in honeycomb core. And these holes is actually to provide a venting path for air to come out. Because when the spacecraft comes to the air want to expand. If there's no expand, it will pop out one of few honeycomb cells. So this is what we call a perforated honeycomb core. So I'm going to pass this a few pieces around. So this one here is partially potted. We cut this in half and we look at the consistency of the potting compound. And there is one which is fully potted. There we go. And this one is a fully potted insert. You can see how this is quite light material. So if you pass around this, there we go. Cheers. What you see that color is actually allochrom color which protects the spacecraft from corrosion. Corrosion? Yeah. But there is free atoms of oxygen which could attack the skin and corrode. But also this particular material or surface finish we use for the thermal protection as well because it has a good emissivity properties. This is similar sandwich panel, but instead of the aluminium skin is carbon fiber, CFRP, carbon fiber plastics. And this visible light, this is what we call it prepreg on the top and the bottom skin. So if you pass this around as well. So actually the configuration of the honeycomb core is on the bottom left pictures. The potting of the insert is illustrated in the middle pictures. And the structure of the spacecraft, what you see on the table is actually on the round side. Interestingly, the top floor, which supports the payload, has nearly 100 millimeter thickness. That was that thick. When I started working on design, I didn't like the idea at all. I said, no way. So I actually designed supports underneath a coastal which would support the structure, and this panel would be 20 millimeters thick. So I presented that design to design authority of the spacecraft in Toulouse, and the guys said, oh yeah, maybe, but they actually did very good work to convince me that it's better to have 100 millimeter thick. But there is a catch there that I'll explain to you later. Right. So this is a top floor double cone. Double cone was designed by a Belgian company and is actually a forged aluminium item. Below the cone is a launch interface rig which directly interfaces the spacecraft. Can I use the whiteboard? Now, how the interface looks to the launcher? The profile of the launcher interface ring looks something like this, and this is sort of 5, 9, 7, 3. So this is sort of diameter of the ring. So that is spacecraft side. This point here, we call separation plane. This is a plane where the spacecraft will be separated from the launcher. On the launcher side, on the launch vehicle adapter, there is a similar, and goes something like this. So these two surfaces are mating. This is just a guiding feature. And then, how are we going to keep these two parts together? How the spacecraft is going to fall off? Well, there is something what we call a clamp band. So clamp band, it's just like my belt. It's a tension a belt, and on one side there is a pyro bolt. So we tension that clamp band, and then when the spacecraft in the space, we send the signal, and the charge in the pyro bolt is activated, and the clamp band is released, and spacecraft is free. Not quite. On the launch vehicle side, there's two push-off spring with gently, very gently push the spacecraft off. So the spacecraft doesn't tumble, doesn't go into, if the spacecraft starts going tumble, it switches into safe mode. And then that is problem to ESO guys. They need to work out, well, what's going on, why the spacecraft is in safe mode. Right, okay. Now next one. Oh, let's take control. Ah, it's here. Okay. This is actually environmental loads. We need to test the spacecraft and qualify the spacecraft. And these loads are coming from the launcher. We are not allowed to fly the spacecraft until we put the spacecraft to these loads. On the left-hand side is also the stiffness requirements from the various launcher. So Vega in the rocket, they had the same stiffness requirements to be after higher than 15 hertz. When I talk about stiffness requirements, what actually I mean is resonance frequency of the whole spacecraft. So if I look at this spacecraft when it's fully assembled, the first mode shape would be just like a cantilever mode, and the spacecraft would just move on one or other side. And then we will have axial mode, and axial mode will be probably one of the components would be alive, would be generating mode shape. So we look what is modal effective mass associated with this particular mode. So you imagine if I put the tropomi on the top, usually goes this side. If I put the tropomi on the then what I get is just a drum effect of this top floor. The top floor just going up and down like a drum. And that was part of the reason why I didn't like that design, but I was army twist, to go for it. But okay. So we're talking about lateral stiffness. But Vega is, because it's a new European launcher, they prescribed very peculiar stiffness requirements to us. And they said the first axial mode has to be between 20 hertz and 45 hertz. So they're giving us a range. So we had to design the spacecraft to stay within that frequency mode. When they had the maiden flight, when they recovered some telemetry from the first maiden flight, they calculate what we call sign equivalent, what is real load, and then we actually understood why they're prescribing that frequency. And the reason is that the Vega had what we called a pogo mode. Pogo mode is just like kids, going on this, spring going up and down, up and down. Actually, the stages of the spacecraft just doing that, and they're coupled together. So the first test we do, we call it the quasi-static test. And the quasi-static is really just a static test, and this inertia initial test. So what we try to do, we put the spacecraft on the launcher, sorry, on the taker, and we excite whole spacecraft. But we don't want to excite the resonant frequency. We don't want to excite that mode at 33 Hertz. So we don't want to excite another mode. So we try to excite the mode at the frequency, very low frequency, far away from the first resonance. Yeah. Yeah. So the first mode, the low level of excitation is at something about 10 Hertz. So at that 10 Hertz, you don't get any resonances. But what you get is you get interface force at the launcher. You get tone and effect of the spacecraft. So we need to come flux under the ring and make sure that this is not gapping on this side, making compression on that side, and on the other side. And that is our reference point actually, that spacecraft interface force. This is it. The quasi-static test is only and only to qualify interface to the spacecraft, nothing else. Then we move to sinusoidal excitation. And the reason why we do sinusoidal excitation is we're trying to verify a primary structure. We need to make sure that the primary structure is strong enough. After sinusoidal excitation, we will shake spacecraft in all directions, in lateral direction, that direction, but also in axial direction. Very, very hectic time, very hectic. For electronic engineers, it's fine. If the black box breaks, okay, we can replace it. If the structure breaks, this is major problem, major issue. So it's very hectic time for us. Then we do acoustic excitation. We take the spacecraft into acoustic room, and there's some horns in that enclosure, and they blow nitrogen through the horns, and they try to excite to actually simulate the noise coming from the launcher. The structure would respond randomly to vibroacoustic excitation. So we would record that random environment, and that random environment we prescribed further down to equipment. And then we look at the shock. Shock could come from various events. It could come from clamp bands, spacecraft separation. It could come from solar rays deployment. It could come from pyrovalves on the propulsion system as well, which they open the flow of the hydrogen going through the spacecraft. It's not easy to analyze that event through our Nastran, our analytical tool, and we normally just rely on empirical data. So what we try to do is we instrument all spacecraft with accelerometers, we simulate that event, and then record acceleration response to the shock of accelerometers mounted on the equipment or on the spacecraft. And we make sure that acceleration response is below the requirements.
Why don't you just throw it onto the floor?
I'll show you. Next slide, maybe. Yeah. Oh. Right, okay. Okay, so this is the rocket. The height of the rocket is about 20.5 meters. And this is now this environment in the numbers. And what you can see is that sine vibration is very low. We are talking about 1G, 1.5G. But that is vibration coming into the spacecraft at this level. So if you have an instrument at that level on the top, we could have 30G, and that is quite significant acceleration response. So an instrument has to vary 30G, and that's quite significant. Right, okay. So we are now still phase C. We haven't passed CDI yet, I'm surprised. Okay, so this is the same spectra, just in the picture. So we can see quasi-static cloud is coming from acceleration of the spacecraft or some gust wing hitting the launcher, and then spacecraft inside the fairings picking up that acceleration. Sun is normally run between 5 and 100 hertz. We analyzed the spacecraft for 120 hertz, but we qualified only to 100 hertz. And the reason is that sometimes at the end of the excitation frequency, we have a mode building up. So during the test, we really don't know whether, so for example, if I have an axis, okay, can you see? Okay. So this is acceleration level, and this is hertz frequency domain. And then we have the first mode, second mode, and then will be something 100 hertz. So in our analysis, we might predict, okay, we have a significant mode, but it's something here. But we are testing only to the 100 hertz. This is our analysis. This is how we perceive is going to happen. In reality, that mode could come into excitation frequency. So this is the reason why we analyze the spacecraft to 120 or some cases 140 hertz, just to account for that mode which would come into excitation range of the spacecraft. Right, okay, and acoustic noise is running up to 2000 hertz, the same as a random from something like 20 hertz to 25, is a wide band frequency oscillation. At that point, all modes on the spacecraft are excited. All spacecraft is dancing, and the modes are interacting with each other. And shock events are, like we said, is coming from events like separation of the spacecraft or solar rays deployment or any other appendages deployment. Bilo kako. Je li to bilo Astrium u Munich ili je bio AIBG?
Onaj kraj Minhena,
AIBG, yes.
Tad mi nije zapravo bilo jasno, baš što ste sad tumačili oko frekvencija, nije mi bilo jasno na koji način vi kontrolirate frekvencije samog, znači, satelita, payloada, kad je on spojen na raketu, jer vi zapravo tamo raketu nemate, imate nekako postavlje kroz koje on puštaju, znači, kroz one velike tube, frekvencije različite da bi testirali da je akustika, ali on kad postavi jedno tijelo sa raketom, reagira drugačije nego kad je sam.
Yes.
To mi tad nije bilo jasno, pa evo sad koristim.
Yeah. Right. So during CD analysis, we build finite element model, and we predict dynamics of the spacecraft at that point. But all dynamics are on the rigid body firmed ground. It's sitting on the ground. You don't move it. What you are talking is about flexible ground when you move. So what we do is we pass our model, FEM model, we prepare for it, we condense a little bit, we use a little bit less degrees of freedom, but still preserving the major frequencies. And you pass that model to the launcher. The launcher has FEA model of the rocket, or FEA model of Atlas or any other spacecraft, and they do couple load analysis. And then they tell us whether our input to the spacecraft is higher than the input is going in reality. Or in other words, whether we're testing the spacecraft to the higher loads or than the input in the spacecraft they're predicting. Yeah? So they do a couple load analysis together with the launcher. Yeah. And it's quite expensive analysis, so they tend to use either once or twice, no more. They will do maybe after CDR, we will pass the model to them, and they will do probably one more time after the test. We would pass the model, and they will look at the levels we tested the spacecraft and make sure that levels are always higher than the flight levels they predict with the couple load analysis. Is that answer to your question? Okay, good. Right. When I was preparing this presentation, I decided really just to look at the three subsystems: mechanical, thermal, and the propulsion. If you look at the other three disciplines, we will stay here till midnight. So this is what we call MTP, mechanical, thermal, and the propulsion systems. So while the spacecraft is in orbit, it's going to be bombarded and debuffed by a thermal flux. Thermal flux coming from the sun, but also reflection coming from the Earth or any other planetary object if you're going on the interplanetary travel. As you know, in the space, there's only two ways we can manage and conduct thermal heat. That is conduction and radiation. Convection doesn't work in the space. There's no matter in the space. There's no molecules. There's no atoms. So we can discard that way of energy transmission. So on the spacecraft, on the S5P, it was really classical thermal equipment we use on the most of the spacecraft. We use radiators on the. If you ever see a spacecraft like the S5P, there is some stuff is covered with these MLIs. So look at this MLI. This is this shiny material, and then some part of the spacecraft are just like metal finishing a color. And that part of the spacecraft is called a radiator. So also thermal engineers, they will look at the coating and the surface finish as a barrier of for the protection of the spacecraft from heating. They will look how they can provide a thermal path to heat to dissipate from the spacecraft. In our particular case, we had a problem. We had a stringent pointing requirements on the top floor. Are we okay, Dan? That for the pointing requirements, the thermal gradient on the top floor has to be only 10 degrees. If it's more, then Tropomi, instead of looking into Brussels, instead of looking towards the Moscow. So we have really to be careful with the pointing requirements of the instrument, as that is the reason why this 10 degrees C is so tight. So we have an analytical tool. What's the name of the analytical tool? ESATAN, thermal engineers use, and they predict the thermal flux of the spacecraft on each orbit. And you can see orbit 1, 2, 3. At the beginning of the orbit is actually a thermal flux due to injection into the orbit. So this is some of the tricks we do to control the heat inside inside the spacecraft. We will have a thermal doubler, and the thermal doubler is actually just a piece of aluminium which is interface between equipment, black box, and the spacecraft structure. And that thermal doubler is, when the heat is generated from the equipment that dissipated, that thermal doubler is a heaty as well. When the spacecraft go into behind the Earth, in the Earth shadow, it still carries a bit of the heat and provides heat back to the equipment. When the instrument hits some minimum requirement temperature, then thermal heaters are kicked on. And I'll show you some examples of the thermal heaters. This is a thermal heater which is wrapped around, which meant to be wrapped about a propulsion pipe. And this is this map wrapped around, and then we put MLI around, and that prevents hydrogen from the heating. And similar heaters we would put on each equipment as well to keep the equipment working with required level. So I'll pass this around as well. Right, we talked about radiators. Radiators could be just part of the structure or could be a standoff radiators, and the heat conduction is provided by thermal piece or a copper between the spacecraft radiator and the spacecraft. Or sometimes we use liquid radiators and liquid pipes, and the heat is traveled through the evaporation for the pipes. Okay, right. To provide the thermal conductivity path between equipment and the spacecraft structure, we sometimes use what we call it a gap filler, because the surface is not perfectly fine, and it's a bit rough. So if you just put equipment on the spacecraft, then there's no conductivity. You need to provide a bit of force to actually make these two surfaces together and to provide the heat coupling, heat conduction, so can be emitted, radiated away. Okay, so we use, there's two materials. We use either indium or tritium or sigma-phase. This is just a trade name for the thermal fillers. Yeah, multi-layer insulation is actually this shiny material. It's like this front surface is a capton, and inside there is many layers of aluminized mirror, and these small films of materials are decoupled with another mesh. So, I mean, if I have a knife or scissors, I could cut it. You can actually see many layers of like aluminium film inside. So I'll pass this around. Right, now we're going to heat the propulsion. On spacecraft, on S5P, we used a propulsion module PN22, which was developed in Germany, I think in Bremen. And this is actually a classical propulsion module. We call it a blow-down propulsion module. And the reason is that we call it blow-down because they use another gas to push propellant, in this case hydrogen, down through the system and down to the thruster. Nanko, do we have the laser here? Is this laser? Ah, yeah. Okay, yeah, I got it. Right. This tank is about 83 kilograms. 2/3 of the tank will be propellant, and on the top would be what we call empty space ullage, and that is filled with either nitrogen or helium. And then there is a filter underneath. The tank is equipped with the heaters as well, and the strain gauges. The heaters we use to prevent hydrogen from the freezing, because hydrogen might freeze below 20 degrees. So to keep hydrogen at sort of temperature between 20 and 40 degrees. The hydrogen travels down to the pipe, and there is a filter here. This is mechanical filter there. And then there is a valve. In this case, we use a latch valve, but it could be a pyro valve. After the pyro valve, there is a flow control valve. So hydrogen is traveling through this branch and then goes to 4 thrusters. Thrusters are only 1 Newton. We don't need much force in a space. There is no air, so you can push it and it goes. The thruster is isolated by 2 solenoid valves. We have the requirements from the launch side to have 3 mechanical barriers for the hydrogen. Hydrogen is highly toxic material. Just a sniff and you're gone. It actually smells like ammonium or something like that, or fishy ammonium smell. In other configuration of the tank, you might have a membrane here which physically separates the push gas from the propellant. In this particular configuration, we have the system which has been qualified, flown in many missions, and it's really just comes in the container, take it out and plug into the spacecraft. This is yellow guy here. This is our propulsion module, but it's just with inside the housing and with MLI. So how are we going to push propellant when it comes to the space? It's okay if you have acceleration, then propellant will come towards this funnel, and then will go down the feed line to the thrusters. But what if you don't? If there is no acceleration? So we use these vanes here. The tank is pressurized to probably medium pressure, about 28 bars. And then that gas displaces the air and the push air towards the walls of the tank, the sphere. Near the sphere, there's these vanes, and then the propellant using capillary action and push the cells down. This is the same way like, if you're sitting in a cafe and you have a glass of the water and put your small straw into the glass, and then when you look at straw, you can see that the level in the straw is not the same as the level in the glass. And this sort of capillary action which they use to push the propellant down to the end of the tank. And then afterwards they use a gas to push propellant all the way down to the thruster. Now there is a problem there. Problem is that we fill the tank up to this level, latch valve. When we activate, the latch valve is wired, so it can only open, it can't close. It's only one-way action. Once propellant is pushed, when the latch valve is open and propellant is pushed down the feed line, it's going to run, accelerate, and hit the thruster solenoid valves. And it could damage the thruster. And this is what is called water harm analysis. It's a similar analysis they do into petrochemical industry. If you have a system with the water and you abruptly call the valve, then the water hits the valves, goes back, creates a vacuum, the water evaporates, and again hits it back. So there is 2 ways to prevent that high peak pressure as the propellant is traveling to the feed line and hitting the thrust. First way is to pressurize a bottom part of the feed lines with, say, 3 bars, and that's what we call it a blanket pressure. So when the latch valve is opened, propellant is rushing and using that gas as a cushion to slow down and to reduce the pressure peak. Now, because the latch valve, you can't close it anyway. You open the latch valve, you rush it, propellant hit the cushion gas. Now you have to open the thruster to vent that gas out. It might be some interaction between the gas and the propellant and the bubbles. So when the propellant with the gas is pushed through the thruster, it could damage the thruster, and you really don't know when you need to close the thruster, because you might be just using the fuel for nothing. What we prefer to do is to fill the tank up to the latch valve, to pressurize the bottom line, and then vent the bottom lines from the latch valve into the space. So just the vacuum in the space will just suck out all the 3 bars of the blanket pressure, and open the latch valve, and we make sure that propellant front or liquid front doesn't damage the solenoid valves. So we require from our supply to qualify thrusters to the level which we think is safe. Okay. Okay. So next. Go ahead. Aha. Aha. Aha.
I osnovno pitanje je bilo koliko još goriva ima propelanta da bi mogli izdržati i da li može izdržati još 2 godine.
Ja.
Oni nisu mogli naći pravu metodu kako bi definirali količinu preostalog goriva. Koristio se nekakav matematički model koji je predviđao.
Yeah. Yeah. Well, the amount of the propellant we carry is based on the delta V. For each maneuver, for each orbit corrections, we need to fire the thrusters, and we know exactly how much propellant is used for each operations. So if the satellite was 7 years, they would actually know how much consumables propellant is used, because they would know at each orbit correction or orbital maneuver they did in the past how much propellant they used. Maybe they could actually look at the strain gauges on the tank, and from the telemetry reading of the strain gauges of the tank, tell us how much pressure they have in the tank, and that will be indication of how much fuel they have left. Or the third option is they could hire one of our satellites which will go there, do rendezvous with the satellites and refuel it. It's being designed. Okay. Yeah, okay, I'm going to have to speed up. I do apologize. Okay, so now we're going to the ATA phase. So we are looking at all equipment is mounting in, it's instrumented, and it's a spacecraft is assembled. You can see the spacecraft. You can see the spacecraft on the right-hand side is open up like a flower pellet. So you have access to the panels on sides to put the equipment, but also you have a propulsion module inside, so you can have access to the propulsion module. Yeah. Danko, this is what you want to see. This is actually what you don't want to see. I'm sorry as well, but this is one of the NASA's satellites. You probably heard about this one. And to my knowledge, you correct me if I'm wrong, is what happened was is the spacecraft was on the turning trolley. The guys, they come out and they borrowed the bolts at the interface of the spacecraft to the trolley, and they told no one about it. They didn't record that, they didn't say anything. Following day, another shift, another group of the people, they come out, they didn't check the bolts, didn't check the torque of the bolts, and start operating the trolley, start lifting the spacecraft, and the spacecraft did the shock test. Yeah, so in Airbus, you are very much aware of these situations, and when we start assembly phase, our quality assurance people have a big say. There is no instruments can be installed in spacecraft without signature of the quality assurance people. And we will have a meeting before installation of the equipment called instrument readiness review. Architects would write installation procedure, and quality assurance engineer would ask, okay, is technician aware of this installation procedure? Have you read the installation procedure? Have you been approved? Do you have kits there available? Bolts, torques, consumables, MLI, and all that rest of the stuff, and then he would approve installation. Yeah, you tell us at what price. Yeah, but there's always problem in assembly procedure. It's always problem. Something doesn't work out. So if there is a problem, we would immediately call NCR, non-conformers. And we would call non-conformers board, sit down around the table, different disciplines, different engineers, and we work out the problems now and then. There and then. All right, okay. So we are now designed the spacecraft. Spacecraft is ready. We went through the installation procedure. Everything's on the top. Payload is on the top. All equipment is on the top. Inside the spacecraft, propulsion module is a test, and we're going to go through the thermal test. So thermal test is really cooking the spacecraft. It's simulating thermal environment in the space. We put the spacecraft into TVAC chamber, pump our air out, and pumping the air from the chamber could last for 2 shifts, 2 days. The pressure in the chamber will be something 10 to the minus 5 millibars, so almost there's nothing inside. And then we will heat it up, cool it down, and heat it up again, and the temperature would vary from, say, minus 100 to plus 100 C. And then thermal engineers would start to switch the equipment on, because equipment inside the spacecraft, the payload, still has to work in the harsh requirements. So they will do on and off, switching off equipment and testing the equipment work in those sort of environments. Then we go to mechanical test. Mechanical test is mostly vibration test in various forms. Somewhere along the line, we would do a propulsion leak test and the maximum operated test on the propulsion system. Before we do environmental testing, we take alignment test of the spacecraft to make sure that the spacecraft is aligned. When we finish the test, we do again alignment and make sure that nothing has moved. It does move, but significantly. It was always settling effect. Right. Okay. So this is sinusoidal vibration. On the top in the pink is in a time domain, and the bottom one is in frequency domain. And that spacecraft is actually a Herschel spacecraft. It's on the shaker, and this is lateral mode. This is the mode shape how the spacecraft looks like when it's excited on the shaker. But we predict that in our analytical tools as well. Right, so next slide is acoustic vibration. This is acoustic spectra on the table tabulators and how it looks on the log graph, linear log graph. That spectra is normally coming, it always comes from the user, simulates the noise the rockets. And you see, oh, hold on just a minute. And then on the, something on the walls, you can see these holes on the walls. Yeah, this is where they pump the nitrogen out and create that noise. It's very noisy. I was standing once outside and it's very, very, very noisy. Right, and this is a shock test. This is separation, simulating separation of the adapter from the spacecraft. Okay, so again on this picture is a vibration test, the spacecraft and the shaker ready for vertical vibration. The middle picture is preparing the spacecraft to go into TVAC test. This piece of the equipment here, we call it a shroud, and this is where liquid nitrogen would circulate and then cool all chamber down to minus 100 degrees. But inside there's a heaters as well. And that is separation of the launch vehicle adapter from the spacecraft. You can see here, this is umbilical cord. This is the cord which provides support, power to the spacecraft from the launcher. And this bit here, this is that clamp. And I hope I'm going to be able to show you, okay. Okay, so now this is baking test. This is taking the spacecraft into TVAC at IBG in Munich. So yeah, you can see the spacecraft is attached to the lower part of the TVAC chamber, and then they push it inside, pump the air out, and they bake it, cook it and bake it. Literally, they cook it and bake it. Right, all gone. Right, now this is high-speed camera, and because the separation of the launcher, actually shock test, and the separation test from the launcher. So if I see this, you'll see actually this is clamp band separated by power bolts, and interface to the spacecraft is released, and spacecraft is separated. And on this side, you can see that is umbilical cord, and clamp band is released, and launch vehicle adapter was released. Well, the spacecraft requirements from the launcher, again, it's all about requirements from the launcher, otherwise we can't fly. It comes that the center of gravity of the spacecraft, particularly for the rocket, has to be something within 5 centimeter sphere from the longitudinal axis of the launcher. So when we design the spacecraft, we run a mass spreadsheet, and we calculate all the time at each design review phase, making sure that the spacecraft center of gravity as close as possible to the launcher longitudinal axis. Sometimes it's not possible, so we need to carry a dead weight. So you can see these blocks here, these 3 blocks there. This is actually a ballast mass, and this is similar test when you go to your service and do your balancing of the car, although the speed of the rotating of the spacecraft is something like about 5 revs per minute. So you can see now the rotation and the checking the spacecraft center of the gravity is within requirements of the launcher. Right, okay, so now this is launch campaign in the pictures. We are nearly there, Danko. So Antonov is arriving, and the cargo load is our S5P. It's taken out from the spacecraft, put on the train, transmitted and transported to the launch site, and then the spacecraft is fueled. One is fueled, the spacecraft is mated with the launch vehicle adapter. Once coupled with the launch vehicle adapter, coupled with the breeze, encapsulated and lifted onto the rocket and fired off. Yeah, this is all about Copernicus program. You can read this on internet, there's a space component and the service component, and all this Sentinel-5 generation of satellite is initiative of the European Commissioner and run by Copernicus. All data are free and available for use. If you want to look any data, if you want to look pollution in your town, you go to the Copernicus website, you register, and you can have a look. And this is some sort of data S5P is looking for pollution and composition, chemical composition of the atmosphere. Now, once we finish the job in the orbits, we'll have mission closeout review, and the spacecraft has to be decommissioned. So all remaining fuel is vented out. The batteries are discharged. We lost RF communication, and the spacecraft is deorbited. So we lower the perigee of the orbits. Deorbit the spacecraft, and we hope the spacecraft will burn down in atmosphere. We have requirements that all objects in the lower Earth orbits, they need to be burned down in atmosphere within 25 years. Right. Okay, and that is end of my run. So